Now let's take a few minutes to focus on low-frequency techniques. Directional subwoofer arrays require a combination of special speaker placement and specific digital processing to preserve summation of bass energy in certain directions and cancellation in others. Here's a system consisting of 16 SP2001 subwoofers with no processing applied to the array. This image shows a frequency response at microphone positions across the width of the venue. Notice how there are huge variations in the response across the room. Arcing can be done by physically arranging the cabinets in an arc shape or by arranging the subs in a straight line and using delay to achieve the arc. Using delay to arc a straight array of subs is preferable for a couple reasons. First, it uses much less physical space to achieve the desired arc. Second, when you physically arc an array, it produces a hotspot of low frequency energy behind the array that would typically be located on stage. Physically arcing the array achieves good results, but the downside is it takes up much more space. By physically offsetting subwoofers, we are essentially creating an arrival time differential at the audience area between the subwoofer. The subwoofers further back arrive at the audience later than those closer. In this image, you can see the same system, but this time with delays applied to the subs to create an arced array. The delays were calculated by using EAW's subwoofer arc calculator. This clearly shows a much more even response in the low end across the width of the room. As you have seen, it's possible to achieve pattern control in subfrequencies through careful use of processing and physical layout of the subs. However, combining these techniques in a gig situation using conventional subs and processors can be time-consuming and labor-intensive. With the introduction of Auto, EAW has managed to combine all of these techniques in a package that makes pattern control of subwoofers a much simpler process. All of the calculations required to achieve the desired coverage of the venue are handled and uploaded to the array by resolution in a matter of seconds. Auto operates on all the same principles as Anya and Anna, though with a few minor differences. The second page of the resolution array assistant for Auto contains a feature called rejection goal. This slider allows the user to decide how much or little rejection they would like from the system. Because even a single Auto module can create cardioid, this slider is useful even when using a single module. Let's look at a few examples of varying levels of rejection and their effects utilizing a ground-stacked array of 6 Auto modules. At 0% rejection, you'll notice we have a nearly omnidirectional response. To achieve this response, the array assistant has chosen to array the modules horizontally, 6 wide and 1 deep. At 25% rejection, the array assistant has chosen to switch the array configuration so the array is 6 modules deep and 1 module wide. With this configuration, we begin to see a notable bias towards the front of the array using only delay to align the arrival of the wavefront at the frontmost subwoofer. This, of course, has the added effect of reducing energy towards the back of the array. At 50% rejection, we add in gain shading to the end-fire array we created, resulting in even greater rear rejection. At 75% rejection, the algorithm will create a cardioid to actively reject sound emanating from the rear of the array, resulting in even better rejection. Our rejection goal of 100% gives us our ideal cardioid using a combination of all the techniques we've discussed in this section. Let's look at an 8-wide horizontal array of Auto and demonstrate the possibilities. Because we have the ability to control each individual woofer within each enclosure, we can easily create complex coverage patterns by simply manipulating the coverage lines and resolution. In the first example, we have our 8 Auto modules set to 100% rejection and 240 degrees of coverage. This gives us a pattern that is very wide, while also providing excellent rear rejection. The system in this configuration does an excellent job of covering our defined coverage area. But what if we receive noise complaints from the north and south of the venue? With adaptive systems, we can tell Auto to narrow the horizontal coverage pattern to reduce the amount of energy going to the side of the venue. By narrowing the coverage to a 20-degree slice of the venue, we eliminate most of the energy to the north and south of the venue while still providing very good rear rejection. The techniques being used here are a combination of cardioid and subwoofer arcing we discussed earlier. To achieve these results manually would be nearly impossible and require a significant amount of time and effort. We've seen that we can easily change the coverage and polar response of an Auto array in real time to help us address real-world problems. Let's take a look at another scenario that may be familiar to some of us, the power alley. For logistical, performance, and aesthetic reasons, it's often desirable to space subwoofers apart, often so that they can be placed alongside or flown next to arrays on the left and right side of the stage. This, of course, creates what we call the power alley, where we get a summation of energy at the center of the venue, but cancellation of energy as we move to the sides of the venue. The result is that the low frequency response of the system is very inconsistent as you move from the center to the sides. In addition to being able to widen and narrow the coverage of auto, we can also direct that energy in any direction we want by adjusting our coverage and resolution. In addition to being able to widen and narrow the coverage of auto, we can also direct that energy in any direction we want by adjusting our coverage and resolution. In these examples, we've directed energy to the left and to the right of the venue. Now let's say we treat those as two separate arrays used simultaneously, but spaced apart. We will still see summation at the center of the venue, but because we've directed energy out towards the sides, we get a much more even distribution of SPL, effectively reducing the power alley and providing consistent coverage everywhere. Here's a real-world example of auto used in an arena. The arrays are spaced apart by nearly 60 feet, yet we're able to effectively eliminate the power alley while still providing excellent rear rejection. Auto, like Anya and Anna, utilizes the same algorithm to decide how to allocate modules to the audience area, weighing the audience areas based on distance away from the array and allocating cells as needed to produce consistent SPL. In this example, Auto is tasked with covering an audience surface which ranges from 10 to 300 feet away, quite a difficult task. Using the algorithms discussed previously, Auto will correctly allocate and direct most of the energy from the array to the very top of the seating area, with just a few cells allocated to those areas closest to the array. The result is exceptionally consistent SPL across even the most extreme audience geometry. Before we finish, you've heard me mention resolution a few times throughout this training. It's our main control and prediction software used for EAW products. Resolution is constantly being updated, and rest assured, when you invest in Adaptive, you're investing in a system that will constantly be improving. By now you should have a good grasp on the benefits of Adaptive and how the system works. If you would like to schedule a demo to hear the system, please contact your regional sales rep, and we'd be more than happy to schedule a day and a time.